Vector function, if vector small I is a function of scalar variable t, then we can write R vector represent as R vector t. If a particle is moving along a curved path, then the position vector R of the particle is a function of t. If the component of ft along x-axis y-axis z-axis are represented as f1t, f2t and f3t respectively. Then ft can be written as ft I unit vector, f2t j, f3t k. Question is, a particle move along the curve x equal to t cube plus 1 and y is equal to t square, z is equal to 2t plus 5, where t is the time. Find the component of its velocity and acceleration at time t is equal to 1 in the direction 3i plus 2j plus 2k. Solution. We have x is equal to t cube plus 1, y is equal to t square and z is equal to 2t plus 5. Okay, then vector r can be formed as xi plus yj plus zk. So vector r can be written as t cube plus 1 I t square j 2t plus 5k. So velocity function is d del r upon dt. We can differentiate with respect to t. Then 3t square pi 2t j 2k when t is equal to 1. Then dr upon dt is equal to 3i plus 2j plus 2k. Unit vector along two I plus 3j plus 2k is 2i plus 3j plus 6k upon root of 4 plus 9 plus 36. Okay, so we can calculate this. So 1 upon 7 2i plus 3j plus 6k. Okay, now component of velocity component of velocity 3i plus 2j plus 2k along 2i plus 3j plus 6k is 3i plus 2j plus 2k into 1 upon 7 2i plus 3j plus 6k, which is equal to 1 upon 7 6 plus 6 plus 12, that means 24 upon 7. Now for acceleration, we double differentiate with respect to t. So 6ti plus 2j when t is equal to 1. Then acceleration is 6i plus 2j. So component of acceleration along with when t is equal to 1. So 6i and 2j 1 upon 7 2i plus 3j plus 6k, which is 1 upon 7 12 plus 6, that means 18 upon 7. Now next question is, a particle moves along the curve r is equal to t cube minus 4t I plus t square plus 4p j 8t square minus 3t cube k, where t is time. Find the magnitude of tangential component of its acceleration at t is equal to 2k. Okay, for solution, here given r is equal to this one, so velocity is dr upon dt, that means 3t square minus 4i 2t plus 4j 16t minus 9t square k. At t is equal to 2, velocity is 8i 8j minus 4k. Now acceleration d2 over dt square is equal to 6ti plus 2j plus 16 minus 18t k. Okay, so at t is equal to 2, the acceleration is equal to 12i plus 2j minus 20k. Okay, the direction of velocity is along tangent, so the tangent vector is velocity, so the tangent vector is velocity. The unit tangent vector is unit tangent vector is this one, so 8i plus 8j minus 4k upon 64 plus 64 plus 16, that means 8i plus 8j minus 4k upon 12. So this is equal to 2i plus 2j minus k upon 3, the tangential component of acceleration. At at is equal to a vector recap, that means 12i plus 2j minus 20k, 2i plus 2j minus k upon 3, so 24 plus 4 plus 20 upon 3, that means 48 upon 3, it means 16 answer. Next topic is point function. A variable quantity whose value at any point in the region of space depends upon the position of point. Is called the point function. Okay, that means a variable quantity whose value at any point in the region of space depends upon the position of the point is called the point function. There are two types of point function. First is scalar point function and second is vector point function. So first, scalar point function. In scalar point function, if to each point P of region R in a space there correspond a unique scalar fp, then it is called scalar point function. Okay, so if to each point P x comma y comma z of a region capital R in space there correspond a unique scalar fp, then f is called scalar point function. For example, the temperature distribution in a heated body. Density of a body. Is vector. Okay, second is vector point function. In vector point function, if to each point P x y z of a region R in space there corresponds a unique vector fp, then f is called a vector point function. It means if to each point P of region capital R in space there correspond a unique vector fp, then f is called a vector point function. For example, the velocity of a moving fluid. Velocity of a moving fluid. Gravitational force is another example of vector point function. Next is vector differential operator del. Operator del, that is this del. The vector differential operator del is denoted by del, and it is defined as del is equal to I, unit vector I, del upon del x plus j del upon del y plus k del upon del z. Next topic is gradient of a scalar function. Gradient of a scalar function. Okay, if phi x y z be a scalar function, then I del phi upon del x plus j del phi upon del y plus k del phi upon del z is called gradient of scalar function. Function phi, and it is denoted by gradient phi. So gradient phi is equal to I del phi upon del x plus j del phi upon del y plus k del phi upon del z. So gradient phi is equal to I del upon del x j del upon del x k del upon del y del z, and phi is the function of x comma y comma z. So gradient phi is equal to del phi. Next topic is normal derivative. Normal derivative. If phi x comma y comma z is equal to c, we present a family of surface for different values of the constant C. Okay, now on differentiating phi, then we get del phi is equal to 0, but d phi is equal to del phi dot dr. So del phi dr is equal to 0. Okay, the scalar product of two vectors del phi and dr vector being 0, and del phi and dr are perpendicular to each other. So dr is in the direction of tangent to the given surface. Thus del phi is vector normal to the surface phi x y z equal to c. Okay, let I repeat. If phi, which is the function of x y z, equal to c, represent a family of the surface for different values of the constant c, and differentiating phi, then we get d phi is equal to 0, but we know that d phi is equal to uh, del phi dot dr. So del phi dr equal to 0, that means the scalar product of two vectors del phi and dr being 0. So del phi and dr are the perpendicular to each other. Okay, dr is in the direction tangent to the given the surface. Thus del phi is the vector normal to the surface, this one. Okay, next topic is directional derivative. The component of del phi in the direction of a vector d is equal to del phi to d and is called the directional derivative of phi in the direction of d. Okay, now del phi upon del r is limit del r tending to 0 del phi upon del r, where del r is equal to PQ. PQ means if we consider those curve and point P is this and normal N which is R and Q is this one, and here phi plus d phi is equal to C and phi is equal to C, this delta N is this. Okay, so del phi upon del R is called diagonal derivative of phi at P in the direction of PQ. Okay, now let a unit vector along PQ be N. So delta N delta is equal to cos theta. That means we can write delta is equal to delta N cos theta, which is equal to delta N dot N. This is 1. Okay, now del phi upon del r is equal to limit delta r tending to 0 and del phi upon del n cap dot n cap, which is equal to n cap del phi upon del n, which is from 1. Del r is equal to del n upon n cap. Okay, so n cap mod of del phi. So n cap del phi, n cap del phi is equal to del phi. Hence del phi upon del r directional derivative is the component of del phi in the direction n cap. So del phi upon del r is equal to n cap del phi, which is equal to del phi cos theta, and which is equal to this one. Hence del phi is the maximum rate of change of phi. Okay, this is the important. If you can find rate of change of maximum rate of change of phi by using this formula. Question is, if phi is equal to 3x square y minus y cube z square, find gradient phi at point 1 comma minus 2 comma 1. So gradient phi is equal to del phi. That means phi del upon del x, j del upon del y, k del upon del z, and phi is 3x square y cube z square. So I del upon del x 3x square y minus y cube z square plus j del upon del y 3x square y minus y cube z square and plus k del upon del z 3x square y minus y cube z square. Okay, so differentiate with respect to x partially, differentiate with respect to y partially, and differentiate with respect to z partially. Then we get I 6xy j 3x square minus 3y square z square and k minus 2 y cube z. Okay, so gradient phi at 1 comma minus 2 comma minus 1. So I 6 into 1 into minus 2 j 3 into 1 minus 3 into 4 into 1 plus k minus 2 into minus 8 into minus 1. Okay, so 6 to 12 minus 12y minus 9j minus 16k. Okay, again I repeat, if phi is a scalar function which is of the form 3x square y minus y cube z, then we can find the gradient phi at a point 1 comma minus 2 comma minus 1. So by using the gradient formula, gradient phi is equal to del phi. So the value of del is I del upon del x plus j del upon del y plus k del upon del z, and the value of phi is 3x square y minus 3 minus y cube z square. Okay, and multiplying these terms, then we get I del upon del x into 3x square y minus y cube z square. Okay, plus j del upon del y, so 3x square y minus y cube z square plus k cap del upon del z 3x square y minus y cube z square. Okay, here we can partial differentiate with respect to x, then we get I partial differentiation with respect to x means only differentiate x and taking y as a constant, y and z as a constant. So we get 3 into 2 6xy and here is 0, and in this term j differentiate y partially. Okay, then here differentiation of y is 1, so 3x square y minus 3y square z square, and k cap differentiate with respect to z, so here 0 minus y cube into 2z power minus 1, that means minus 2 y cube z. Okay, we find the gradient phi at a point 1 comma minus 2 comma minus 1, that means the value of x become 1, y become 2 minus 2 and z become minus 1. Put these values in this function, then we get I into 6 into 1 into minus 2. Okay, and 1 minus 2 1 minus 1, this one, and calculate these terms.